I would like to turn it over to tonight's presenter, Joe Wright.
Well, thank you for being here, and thanks for the people that are listening online. By the way, one of the things that's over there are these little, it's called a trading card. It's solar system objects. That's pretty handy, especially if you have kids or your own interest. So grab a pack of them. We'll put that back over there. And there's some other items over there, NASA sticker, just some knickknacks that we get from JPL and different organizations. I don't mind any questions. If I say something that you don't understand or wasn't clear, let me know. I've been in the same situation, especially in one of my college math classes, differential equations that I didn't understand, and I knew I better ask because it was a required class. So I understand about not knowing things or not hearing things clearly. Like I said, thanks for the Colburn branch having us here, and Beth hosting us online. We do several of these a year that are online, so it is a little bit different, but still enjoyable. This is by no means any kind of strict formal type of presentation. You can ask questions anytime. Give me a moment maybe to finish the sentence so I don't forget what I was going to say. We've all been there. And hopefully enjoy the evening. In fact, up here on the front table, I know you can't see them online, I actually checked out a couple of books last week that are brand new to the library's collection on the Webb telescope. So they have some books here on the Webb telescope in their collection. This image that you see right now, you're going to see it again. I think this is probably the most recognized image that NASA, that Hubble and Webb has taken. It's called the Eagles Nebula M16. The M stands for this guy, there's a comet hunter, Charles Messier. He was looking for comets. He'd find these faint, fuzzy things and mark them down where they're at. So when he came by again, he'd say, oh yeah, that's not a comet. I can forget about that. So he's more famous for finding about 95 of these things, 100 of these things, objects in the sky, more than he is for any comet that he had discovered. Yes?
Here are the clouds,
Yes, and we'll talk about that. They're
like what we have in the sky.
Well,
same thing.
ours are mostly water vapor, plus whatever pollution is up there. Gas clouds, mostly that you see in space, is hydrogen gas. It's the most abundant thing in the universe, and that's what condenses down into stars. So, and that's one of the things that Webb is going to be studying and imaging. And there's, this changes weekly, all right, as far as what their images that they're downloading. Just today on the way out here, my wife and I, she said, hey, did you hear about this? I said, yeah, I found it while I was in class today while the students were working and started downloading some information on it. It was the recent images that I had found. A little bit about myself. How did I get in like infrared? Well, one was the person we worked for at the University of Arizona when we teach out there. He was an infrared astronomer, and he was my mentor and helped me actually sign my papers as a rep, gave me a reference. I flew missions on NASA aircraft. The SOFIA stands for Stratospheric Observatory for Infrared Astronomy. Basically, this 747 flew up to 50,000 feet high and only imaged in the infrared at night. And so we were issued astronauts jackets for flying on that. And that's probably one of the biggest memories I'll ever have. And then, of course, the others are Maven and Webb in the middle. And down at the bottom, Spitzer, which you'll hear a little bit about. That was the previous infrared satellite telescope. If you're local, I'm the manager of the observatory at UMKC. It's open free on Friday nights, May through October. I would say sunset, but that varies. So check the website at askc.org. Right now, we're opening around 8:30, 9 o'clock because, as you well know, in Kansas City, it doesn't get dark, especially in June and July, until about 9:30. It's absolutely free. We have 3 telescopes to look at. And in the center picture, there's the largest that's handmade Took the guy about 10 years to make that. He had it in his backyard at 70th and Troost, just off Troost for many years. And he made it for his wife. She was the astronomer. Imagine, yes.
Do you have to sign up?
Nope.
Go there? You
Open.
Show up?
Just show up. Best thing to do is at 51st and Charlotte off of Rock Hill Road. You'll see a parking structure. Park on the 4th level of the parking garage. There's a pedestrian bridge into the building, and elevator, stairs go up to the 4th floor. Then in the stairwell, you'll see the steps that go up to the roof. There's no elevator to the roof. And that is an excellent scope for looking at solar system objects. Now, we're not in dark skies, of course, being inside the city, but we still pick out some of the faint stuff like the galaxies, the nebulas and stuff like that are brighter. So no reservation or anything. Just be there before 10 o'clock because the doors are locked at 10, but if you're on the roof, you have till 11. Yes.
So if it's raining or,
If you can't see the sky, we can't either.
okay,
and-
so pick a Friday to go when the weather.
Yeah. A Friday, I try to post on whatever it's called now, Facebook, Twitter, X, I don't know, keep up. It's Royal Hall. And they're, like I said, at 51st in Charlotte and 52nd, there's the parking garage takes up the entire block. And you'll see it. Both UMKC and the ASKC have maps to it on their website. And open door. We ask you to sign our guest book and do our demographics, that whatever box you check for age and stuff like that gets turned into a 0 or a 1 in Excel so we can count the numbers and turn it in for grant reporting. But we have the 16-inch there. Then up in the upper left, the first telescope is a 14-inch. Then you got the 16 back behind. Then farthest back is a 10-inch. The other two, the foreground one and the background, are computerized. We can actually move them around with the computer. That one there, the big one, is all manual. So you have to kind of know your sky, especially as light polluted as it is down there just off the plaza. But it's a fun time. And I can never say how many people will show up. It could be from 25 to 125. Just depends on what's going on. All right. I just tossed this in. I always thought about Walter Cronkite when I was growing up as a kid. On Saturday mornings, we watched You Were There when he done history stuff. So a little bit background. Light. I think everybody's heard of Isaac Newton. All right. He took a prism, round piece of glass, and passed light through it and got the rainbow. Then nothing was really done after that. But he did make his own telescope. Galileo's was a refractor, kind of like our eyes, had the lens. Newton made one that had a mirror, and they call it Newtonian. Then some years later, this guy named William Herschel, him and his sister Caroline were astronomers, and he's wondering, what is the temperature of light? So he set up in his window a prism up over his head behind his left shoulder there that brought the light out, spread the light out, just like that rainbow we had the other day. If you got to see the double rainbow, I think it was on Saturday. Same principle, okay? It brings out the light and its components, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And he was noting the temperature. Then he slid the thermometers, I guess, to the side and was doing something. And he noticed the temperature kept increasing, but there was no light. And he called it calorific rays. And that was the infrared. And then again, nothing was done for many, many years until in the late 1800s, we started developing instruments that could actually detect infrared. Now, everybody in here knows infrared very well during the wintertime. When you get in your car, when it's 25 degrees out on a sunny day and it feels like it's 55 degrees in the car, that's the infrared heat from the sun warming us up. These were the first airborne observatories, going from the top one, Convair 990, Learjet, the C-141 Starlifter, and then the bottom was the 747. which was retired by James Webb Space Telescope about 8 years before its program was set to end. So they retired it earlier. It's down at the Pima Air Museum in Tucson, Arizona. And why do we want observatories on mountaintops and then in the sky and then ultimately in space? It's the atmosphere. As we were saying earlier about our clouds are water vapor. Water vapor traps heat. All right, so the infrared rays don't make it through as easily through the water vapor in our atmosphere as it does when you start getting up 45, 50,000 feet or up in space where there's no atmosphere whatsoever. And on Sophia, we figured that we were above 95% of the water vapor in the atmosphere at that altitude. So we have them on mountaintops, Mount Lemmon in Tucson, Arizona. Of course, Hawaii has the Keck telescope. And then down in Chile, where it's very dry, they have them up in elevation where the atmosphere is thin. In fact, if you've ever been out like to New Mexico or Arizona, you'll notice how during the daytime, how blue the sky is because it's drier than it is here. It's very remarkable. So we've been putting stuff up for many, many years. Then there was the great observatories. This was a thing program NASA said, okay, what 4 observatories can we come up with to put in space? Excuse me. And I mention this because you'll hear people say, well, the Webb was Hubble's replacement. Well, no, it wasn't. It was its descendant. Okay, Hubble was white light and a little bit of infrared, where Spitzer and Webb are infrared. Okay, and we can't see it. We can detect it by feeling it, the heat, but we don't see it with our eyes. So it wasn't a replacement. We had them for X-ray, gamma rays, of course, infrared and visual. And we all remember the kind of images we got after they put the contact lens inside the Hubble because the mirror wasn't ground right. They figured out how they can do that, and then the images were stunning. And so here's some images from Spitzer. And I know I'm going to be repeating this earlier, but probably wonder, why do we need it? Well, just like firefighters, pilots, they use infrared to see at night. Firefighters can find somebody laying on the floor because of the body heat. The police use it in helicopters to find criminals hiding. And sometimes if you ever watch some of the shows, you can actually see their forward-looking infrared that they would have, the flare. Well, heat gets past the dust and gas that is out there. Think about driving through the fog. You turn on your bright lights, all you see is this white cloud. But if we had a way to pick up the heat from the exhaust of a car in front of us on a heads-up display, we can actually see that car then without any light on it whatsoever. We would see the heat from the engine and the tires and the exhaust pipe. Now, Hubble's deep field here. I don't know if anybody here or online has gone out and looked at it, but think about looking at let's say the most boring spot in the sky that you can think of. There's not going to be much there. Now let's pick somewhere in the Virgo that looks empty. And we're going to take a picture for, I don't know, 98 hours. And our eye dumps images real time to our brain. But when you do imaging in astronomy, you can stack these photos. So instead of like in the old days when we would use film on a telescope, where you take an hour, hour and a half long exposure, well, let's take 10-second exposures and stack 10 of them, and you get more resolution. So they did that with Hubble, and they were surprised. Everything you see in here is a galaxy. It shocked them that they thought, well, they wasn't going to find much, and they found more galaxies than they ever imagined they would in that part of the sky. And Webb's going to recreate that because we see it in different light. This is basically a white light photo. Now, there might be a few foreground stars, just like if you had trees when you're pointing to the horizon. Yes.
Sorry, can you tell me what makes up one galaxy? So what am I seeing?
Well, it's interesting. It wasn't back until about the 1930s they started really thinking about things as being galaxies. They were faint and fuzzies to many of them. So a galaxy is a collection of, let's say, 1 billion stars or more that have a common gravitational center that they spiral around, you know, as believed, a black hole. And that's the engine of the galaxy. Okay, the engine of our solar system is the sun, like we go around it. So right now, you're going around the sun 66,000 miles an hour. But you're moving so many million miles an hour in the galaxy as it spins. And back to the hydrogen gas, since it's so abundant, you have groups of stars that are formed out of the same hydrogen gas. Well, don't know where it came from, how it did. Somehow there was some kind of a shock wave or explosion that started condensing gas, then started into forming stars in that gravity, and black holes eventually started attracting things. But galaxies are basically billions and billions of stars that spiral around a common center. And there's all different kinds of shapes of galaxies. And that's one of the things that the Webb is hopefully going to help us understand more. This is called the electromagnetic spectrum, as it says. So think that the entire range of light, what we call light, is from gamma ray to radio waves. And most of you know those in between, especially radio, microwave, if you've made popcorn lately, infrared, ultraviolet for the sun, because we have to put on our SPF 1000. And then on up, seems like that's what they're getting to X-ray, dentists, you know, doctors, and then gamma rays. Gamma comes from exploding stars. It's about the only place it comes from. Everything else comes from different sources, right? So imagine that whole thing across there is a piano keyboard with 88 keys. You can see over there where white light, visible light, is spread out into its different colors and how small of an area, a region that it actually occupies on that entire spectrum. So that's about 4 keys of a piano, if there's 88 keys on a piano that we see. That doesn't mean we can't sense them. Even animals can sense infrared, right? Snakes use their tongue to pick up the heat from prey. But we can see different things with those different wavelengths. Also, think about this. They used to call, one joke was to call infrared astronomy and study of that stuff the old, cold, and dead. All right, because if you're looking at that stuff, it's so far out, you know, it's cooling off. Some stuff might be dead in a sense. But as it's expanding, just like what we call a Doppler effect, that's the train and sirens. As it's coming at you, it's a higher pitched. As it passes you and starts going away, the waves get stretched out and it's a longer pitch. Same thing happens with light, that stuff shifts towards the red if it's going away, shifts towards the blue if it's coming at you. And it's that stretching that we're looking for of the infrared light left over from just after the Big Bang. And I've already mentioned this, firefighters and stuff, people. I've even used some night vision goggles. When my scouts wanted to play hide and seek, we thought, okay, we'll play, but they didn't know we had a pair of night vision goggles. Always got to keep ahead of my boys. And so, and you've seen some of this on TV. You can even hire companies, they'll go around the city, they'll advertise on TV, we'll do an infrared picture of your house to show you where the heat's escaping it from during the wintertime to show you where you need insulation or something. So where'd the name come from? James Webb. He was the second administrator of NASA from 61 to 68 when we started launching. Mercury, Gemini, the way they say it. Around here we usually say Gemini. And of course, the Apollo program that landed on the moon. So he was over NASA when all that happened. In fact, there's one of the, I forgot the actor's name, that if you watch Tom Hanks from the Earth to the Moon, there's Webb's character is in part of that, why they're discussing launches and stuff and about scheduling. Now here's the mirror of the Webb. And later on, there's going to be an image showing you how much bigger this is compared to the Hubble. Okay. And I see I missed, I thought I actually transferred this. I was recalculating this into English units. So approximately it's 6,200 kilograms. All right, kilograms, 2.2 pounds. So that's getting close to 13,000 pounds, right? And that's assembly. One mirror segment was, with the back on it, the frame, was 30, let's say 40 kilograms, about 80 pounds. So this thing's heavy. And you're seeing when it's opened up. Now, what I like to tell young kids, this is a giant transformer like one of their toys. This thing folds up, and you'll see a picture of it folded up, goes into the coning the nose of a rocket. All right, and then has to unfold, and it has to work the first time. And you kind of get a scale by the guys down here on the floor, how large this is. And none of them wearing a hard hat underneath that thing. You think they would have to. And there's 18 mirrors. That's the most important things. Oh, except one thing. What do you think that coating is, that yellow coating? It's gold. So how much gold do you think it takes to coat all those mirrors? About the same as the weight of a golf ball. Take the weight of a golf ball, that's how much gold is on all those mirrors.
Very thin.
Very thin. That's why sometimes astronomers get touchy when people want to touch the mirror in their telescope, because the oil on hands and stuff can actually hurt it. So it's very thin, thinner than a hair. And gold is a good conductor of electricity and heat too. Oh, there we go. There's the Hubble on the left, Spitzer on the right, and Webb in the center. It's big. It's big. And the question we get asked all the time is, how far can you see with the telescope? Well, it's a kind of a political question. You notice politicians never say yes or no. Is it a bright object that's really faint, far away, or is it a dim object that's really close? It really has to do with how bright it is. So the larger the mirror, the more light you collect. If money was falling from the sky, would you want a wheelbarrow to collect it or a Dixie cup? We want the biggest thing we can to collect more money. Same thing with a telescope mirror. And a little more information there about the Hubble. It's still going, by the way. Spitzer ran out of what's called the cryogenics, the stuff to keep it colder. They talk about, just like with the Apollo program, the space program, how many people did it put to work all those years? Same thing with this. This isn't all the companies. It's a round the world thing. Of course, ESA is the European. STSC is the people that control many of the telescopes. And the University of Arizona up there, I especially want to mention that because I work there, my wife works there. That's who made some of the cameras for these telescopes. So you got to build it, test it, launch it, deploy it, and wait back to see what happens. If it works, which it did. So to give you an idea how large this entire thing is, it's about the size of a tennis court. Wherever they had, like installations working on parts of the telescope, they actually took this around. It never did make it near Kansas City, but they took this around and put it up at places so the employees could see what size it is, get the full impact of it. So it is rather large. It's not like one of the little rovers that's on Mars. Hubble is about the size of a school bus. This is the size of a tennis court.
And the different layers that are there,
Mm-hmm.
is that for like shielding?
You're absolutely right. And there's another image of it. So I said this thing is collecting heat light, right? What's the biggest generator of heat that we know of right now around us? The sun. So you don't want sunlight getting on the mirror or the instruments. So just like in the Victorian day, the ladies carried a parasol, right? To keep the sun off of them. This one has 5 layers of it. You get it down as close as possible to the temperature of space. And it does very well. And it was very complicated.
So it actually looks like that in space with the layers behind it.
Yep. Now,
And the telescope pointed away from the sun.
right. Now, it's hard to find a picture where it shows how it's actually positioned in space. They show it this way because it's the easiest way to get a picture of it.
Oh.
But it's actually rotated 90 degrees. So the sunshade is always towards the sun. The telescope's on the backside away from it. It's not sitting up this way because then it would be susceptible to the sun. And it took me, when I first started years ago back in, gosh, what was it, 2004, 5, when we were out there, that, I started wondering, okay, how does that keep the sun off of it? Then I got thinking, oh, it's got to be turned 90 degrees. And it has basically about 4 different main components. Of course, you have the optical system, the mirrors. Okay, there's a mirror, secondary mirror that shoots it down through here, through the primary, into the instruments, just like many of the telescopes we have around here. Then it's got the instrument package back here, the sun shield, and then the bus. Okay, the bus is the hardware, propellant, things like that, gyro, keep it pointed in the right direction, because that's important. Let's see. Nothing new there. I was a little confused because I could remember doing the calculations this morning, and I don't know where that slide went that I thought I put in here, where I converted everything to English units. The distance where it's at, 1.5 million kilometers, that's just under 1 million miles, 980,000 or so. So what's way out there? There'd never be any repair mission to this. Does anybody know how far the space shuttle could go in orbit? The same distance that the Hubble is, 300 miles. It wasn't really designed to go any farther than the Hubble Space Telescope. Good thing, because they took the contact lens up there and put in it.
Most expensive service call ever.
Yeah, yeah. Oh, I'd like to have that, send that invoice in, wouldn't you? But it worked. So we're very happy with it. I think it was money well spent. Here's like a X-ray of it where you can see the back part of it. Okay, the blue frame is the instrumentation stuff. Of course, the lighter is your mirror cells that are holding the mirrors on. Then you got the tube down through here to the bus, and then of course the sunshades and its arms that come out. Basically, there's an image. Yes.
Does the light ricochet off the gold mirrors?
Mm-hmm.
This piece out here, that's another mirror.
Yeah, sorry. I thought I was going to go backwards. Right. So
It goes out there, it shines on it, and then it goes back in to.
right. And there's going to be another picture. So basically, the gentleman's asking, what is the light path of the light coming to it? So the primary mirror, the gold one, okay, that's the primary. Any telescope, you talk about size. If it's a reflector, which this is, you talk about the size of the mirror. If it's a refractor, like the old baseball bat ones that you see all over the place, that you want to get a reputable one if you buy one that has the long tube with the lens up front and the eyepiece in the back, you look straight through, that's a refractor. You always talk about the size of the front end. So that's the primary. On mirrored telescopes, you have a secondary, which is here on the Webb, that the light from the primary bounces, reflects up into the secondary, then back through a hole or a spot in the mirror to the instruments. Okay, the ones at UMKC that I showed earlier, okay, those are all mirrors. Okay, so the foreground and the background one, the 14 and the 10, actually has a hole in the mirror, just like that, where the light comes through it. The other one, which the big one, the 16-inch one, it's like Newton's telescope. That's why it's called Newtonian. So it has a mirror at the bottom that shoots the light up to the other end, to the secondary, that's at 45 degrees, and the light comes out the side where you put the eyepiece. So, but you're right, it bounces off there, comes back into the instruments, and then it's gonna go, and I have some animations, shows this light path, because, you know, you're just not putting one instrument to check things out there to measure. You're trying to send, I don't know, you know, you're trying to get as much in it as you do as your to-go box at the restaurant, okay? So you only have that one trip, right? So you try to put as many instruments to share that light, to split it up, so you can measure different things. And we'll see that here in a moment. So there's another picture. So yeah, that's the primary. Down in here is where it would go into the instrumentation, down in the center there. And then you can see some of the gantry here. Here's the holding of the upper one where the secondary mirror would be. And then it comes right back into there. And all that structure, by the way, in the top image on the right, is made out of beryllium. And I always remember beryllium from the movie, what was it, Galaxy Quest, where they were trying to get the beryllium spheres or something for their spacecraft. Same material, okay? Very rare, very hard to machine. And it was explained to me, Henrietta, that they didn't trust the CNC machines to automatically cut them out, that they brought machinists out of retirement because when they're working with material, they know, hey, I better not put any more force on that bit, it's going to break, and that stuff's expensive. Machine, it doesn't know that, it's just going to keep pushing until it goes through, and if something's wrong. So we were told that they brought retired machinists in that had done that kind of stuff to make this, the arrangement there, the structure for the mirrors and stuff. Okay. And I am going to say, so it took 30 years to get it up into space. That's from the time that they started designing it, started building it, started testing it, because they had to bring pieces from different parts of the country together and put them together and see that they worked together and didn't fight each other as far as having problems with software and stuff. And it was $10 billion over that course of years. So a long time. So there's 4 instruments basically. You have the NIRCam, that's near infrared camera. You have then a spectrometer that's going to look at the spectra of different objects, just like you saw with the Newton doing with the lens and Herschel. Okay, we can look at spectra and see, okay, that star might be burning more helium than hydrogen, or it's getting close to, it's getting ready to go into supernova because it's already down towards iron that no star can fuse, and then it explodes. So we look at spectra to tell us stuff. Also, if you're looking at planets, okay, let's say a planet like Pluto goes in front of a background star, okay? Its sunlight passes through the atmosphere. With that spectra, you can tell what kind of stuff is in the atmosphere of these planets. And that's what they're hoping Webb will be doing with the exoplanets, which might be giving away some other future slides, but that's what it's doing. Then there's MIRI, which is the mid-range infrared. Okay, so there's near infrared, infrared, and then far infrared. depending on the actual wavelength of light. You need a different detector for each one. It's not just like our eye sees all the visible light. It has to have a set wavelength of light that it detects. And then the bottom one, that's its fine guidance system. So you have to have a way to be sure you're pointing accurately at your objects and targets that you want, and also to maneuver it, do that. Because as this is going around the sun with us, you have to rotate it, like I guess you'd call it yaw, for you to get the object, because it's going around, think of it going around sideways, and you say, okay, I want it, it's over there, I can get it, or do I need to rotate it back this way to get over this way? So as it's going around, see, that's how you get your different views, different directions. And there's, let's see, when did I have that there? So there's your three ranges. Basically, that word up there, microns, okay, that's 1/1,000,000th of a meter. That's how short the wavelength is, 1/1,000,000th of a meter. And in the days back in the 70s and 80s, we used to call wavelength by angstroms. Then they went to nanometers and microns is the current system that they use. And then that's the wavelengths from 1 to 30. And it gives you an idea of what each type will be used for. The lowest one, visible. Cooler stars, the red stars, galaxies, and dust that is transparent. And then planets, comets, and asteroids, warm dust. Okay. And then what they call protoplanetary disk, where a star is being born, or a planet. This is actual images of what each one of these looks like on this entire instrument bay. All right. And you can see where they're sitting on the back of that telescope. There's the actual near cam. Okay. I don't know. It seems like more younger people are into how many megapixels is the camera on your phone? So 40 megapixels, pretty good size file size.
Big is that camera?
Um,
Is it the size of your hand or?
Oh, it's bigger than that. It put a couple of these, about 4 of these tables together. It's a fair size.
Okay.
But it's got quite a bit on it. All right. There's a color filter wheel. One way of dividing light is not only a prism, you can use what's called a diffraction grating, where you have something that's got like 1,000 lines per 1/8 inch or something. So, and they can have 4 chips on it, basically, where they can put something on a different shot on each chip. So they can do more than just one thing. Here's a light ray trace. Okay, this is how when the path of light comes in, you'll see it go through the different parts. So there's going to be half silvered mirrors where some light passes through, some reflect to another instrument, the diffraction grating to split up the spectra, filter wheels like the one that's rotating to see what it can be filtered out, to see what kind of stuff, what kind of components are made up, what they're looking at. So basically, they're trying to put as much in a small package as possible to do the most.
Okay.
So it is a giant transformer. And it's not easy. This was new. They had to invent technology to build this thing. That's one reason it was so expensive. And then, guess what it comes out as?
So what portions are they,
Zeros and ones. What's that?
what portion are they refrigerated?
Well, they're going to refrigerate the receptors, okay, the cameras and stuff. On your phones, you don't worry about having electronic noise and stuff like that. On observatory cameras, and the earthbound ones and space, you want them cold, because the colder you get the chip, the less background or electronic noise you get, or stray heat coming in. So here we might put, like on Sophia, we put liquid nitrogen and helium through the camera to keep it cold. Up space, you know, they can use space. It's minus, you know, 370 degrees below zero. So this thing actually works just 50 degrees above absolute zero. So they're keeping it as cold as they can with those sunshades because they want to pick up, they don't want heat from some stray source. Okay. It could detect, if you blew out a match on the moon, it could detect it from Earth, that kind of stuff, or farther. So it's very, very sensitive. In fact, you can do this when you go home. I know it's mostly with the Android phones. Turn on your camera, get some of the remote controls in the house, have someone point it at the camera and press different buttons and see if you see any flashing light. Your eyes don't see it, but the cameras can pick up some of the infrared light. They actually had to put filters in because they were too good at collecting infrared light, kind of like the X-ray machines at the airport. They had to tone them down, right? Because they showed too much. Okay. Uh-oh. Oh, here we go. All right. I hope I didn't skip anything there. So diffraction gratings in the middle here, they can use to split the spectra out instead of using ground glass. That can be more fragile in space, right? And then they can pick out the object that they want on different areas of the detectors and then see what they're made out of. Is it hydrogen, helium, nitrogen, all that kind of stuff? Silica, is it a planet coming together? The fine guidance system. Kind of Larry to push the button after it wouldn't go back. Okay, so, okay, we have to maneuver this thing. We have to keep it pointed while it's going around, traveling, okay? The Hubble can go around the Earth basically in about 90 minutes, let's say. Okay, you have to keep that thing pointed at the same object as it's moving. That's hard to do. But if you have a good guidance system, they say, okay, on the guidance system, I want you to follow that star to stay on it no matter where you're going. And that's what happens basically, that you got one part of the chip says, okay, I'm going to be pointed at this as my guide scope, is my guide star. But the main scope is going to be instruments pointed over here. And as it moves, that moves the telescope to keep it on point. Even on Sophia, you can see not the camera moving. It was the airplane moving around the camera. The camera was staying stationary. You can see the airplane move around it just a little bit as you flew. It was really cool. This is just another animation of how the guidance system works. What happens with the light as it comes in. Bounces off of a mirror. Goes down, gets filtered. And I'm sure there's more than one check that they do to make sure it's guiding correctly. You have to have redundancy in case something fails. A lot of times that's why Navy airplanes always had two engines. You didn't want one to fail. If you only had one and it failed over the ocean, you were going to get wet. And imagine, then it compares them. So, okay, you're correct. We're good to go. And the gratings again, I mentioned. Let's see it from this side. And detectors, so it has redundancy. Photometrics, we do that here, okay? I'm looking at something, how faint is it? How bright is it? Also, how fast is it moving? That's photometrics. We take a look at that stuff, even down at POW. When we're imaging asteroids, we would do the photometrics to find out where's it in space, how bright is it? And after several images, we can actually find out which way is it moving and how fast. The sunshade, the gentleman was talking about. Think of it as a super heavy-duty Mylar. It's got to be light, got to fold up, and then it's got to open up the first time. Not only open this way, but also unstack, because there's 5 layers that are compressed together. So it all folded up. And then you got the layers here. Here's where it goes into the nose. Okay. This is the launch. Down near the equator, right? Because it's easier to launch from down there. Harder to get to if you want to watch it, but. And it's in French, by the way, that's who's launching it, so. Oh, what day did this launch? Anybody know? Christmas Day. So you know what a lot of astronomers were doing Christmas morning? Watching TV our internet to see this thing launch. Because I remember how many times it'd been pushed back. Now, of course, when it got into space, we couldn't see it anymore. There's no drone to follow it out there. Okay.
1.5 million miles were
Kilometers.
kilometers,
Just under 1 million miles.
so it's not quite the distance to the moon.
Oh, that's farther. The moon's 240,000 miles. They're about that far on the maps, I tell my scouts. Deployment. Now this, we can see how things unfolded.
This information.
Yeah, yeah. It's like who's out there in a spacesuit taking pictures? Now see if we had a shuttle, maybe. And I like this one because it names what it's doing. And of course, they didn't do this fast. They went through checks to make sure everything was running properly. Okay. Now this is where we need sound when sound effects that if this was unfolding as it ratcheted out. Yep, the scope came up, the mirror came up. There's the unfolding of the sunshades. Origami is what I like to call it.
So it folded the entire, or most of the way that it was traveling there.
Yeah.
Okay, for some reason I always thought it got there and then unfolded.
They think it might have already been struck by a small meteoroid. Now they're going to separate. And of course, there's no wind out there to affect them.
So what made them think they got struck by a meteor?
I guess they had some kind of way of detecting it. I don't remember what part. I'm sure that they can tell if there was damage to a mirror, which mirror it was, and how much maybe degradation it had if it was a really bad impact. And this actually has, I think, the animation of its orbit when it gets out there. And there it goes. And that's where it sits. So this point is called the Lagrange point. There's 5 of them. Think of it as some point away from Earth that you can park something that is, in all essence, locked to the Earth to go around the sun with the Earth as we go around. Kind of like taking a hammer ball on a cable that's standing out there straight, and as you rotate around the sun, it goes with it. Takes less propellant. Less propellant, you don't have to put so much in it. Reduces the cost and the weight of the thing. So it's going to be there, but they'll have to do some little course corrections and some rotation of it. Mm-hmm.
And gravity holds it.
Yeah, pretty much. And also,
To the sun and to the
yes,
Earth.
yes, and our Earth helps shade it from some of the light from the Earth. Not a whole lot, but a little bit from it. So, of course, when it's going around, it doesn't. But I mean, it's in a good spot. It's going to be there. It's a good idea to use that. And they've
So
used
it
some
doesn't
before.
have any type of propellant
Oh
or
yeah,
anything?
it's going to have some maneuvering propellant. Usually that's a gas, like it could be helium or something. It doesn't have to be like you think on Earth, having something that has to combust. It just has to push it. You know, that's what the
Okay.
right. If you ever look at the Apollo service module, they got the little cone ports on the outside all the way around it so they can move the spacecraft with just puffs of gas. Okay. How do you use the thing? You put in a proposal. Anybody can put in a proposal. All right. There's already been 2,300 proposals submitted. It's a total of 75,000 observation hours. That's how full it is already. 10-to-1 oversubscription rate. So they're getting, just like Hubble. Hubble produced more papers than any other instrument or spacecraft that's been launched. Right? Some places, depending on what they're doing, get more hours. Okay, up there at Cornell, you know, they're looking at galaxy formation and stuff, so they're going to get more hours because it takes longer observations for that kind of stuff, farther away. What are they going to be looking at? This is the science. The cosmic dawn. When did it happen? Just after the Big Bang. Like 300 million years or less after the Big Bang. That's pretty close when you're talking about billions. Okay, exoplanets. Living planets, like the one they've just been talking about in the paper where they've detected something in the atmosphere that only life could produce. And our own solar system. We're still studying our own solar system. In fact, I just read today, I guess Russia launched something towards Venus and it failed or something, and it might be crashing to Earth soon. I read that while I was here this evening. That's determine how galaxies are formed. How are planets and stars formed? What causes the shock wave that causes that gas to start spiraling? Because you have to condense that gas in a star down to where it gets to, was it 18 million degrees before fusion starts and turns it into a star. What about the dust of that stuff that's left over? Okay, we're looking through the dust and gas that's in space. Okay, we're going to be looking back in time. How are things formed? A supernova. Right? What does that do? What elements are going to be shot out into space from that supernova? Gold, platinum, the other rare earth minerals we have on Earth. How can it affect us if it's close to us? If it's too close, it's not going to be very good for us. Galaxies. We know that they collide. Our galaxy will be colliding with our closest galaxy, the Andromeda galaxy, in what, 5 million years, 5 billion years? I've got insurance policies if you need one. But the stars are so far apart that they probably won't even hit each other. It's not like a train wreck. We're going to be looking at what happens during a gamma ray burst. Okay, in fact, let's see, this would be April 23rd. Most distant object found, supernova jets. Okay, we're going to be looking at those with Webb, better than any other telescope. Earth, the planets and stars, like I said. The gas, the rock and stuff left over after the stars are formed. If you look at Orion's sword with a pair of binoculars, download Stellarium, a pre-planetarium software, find when Orion will be overhead, take your binoculars outside, look in the sword, and you're going to see this gray cloud. That's the gas. That's the hydrogen gas where stars are being formed. And you'll see these bright stars in the middle of it. All those stars are from the same gas, okay, because we come from the same gas cloud. Most stars you see are binary or triple stars in the sky. They're not single stars. And then left over from that would be the dust that condenses down into a planet. Or what happens when something collapses? What we can't see right now. Maybe it's going to help understand dark matter, dark energy. There's a lot out there that's we have no idea about it right now. There's still theories. How do the galaxies, I think that one is called the mice, because it looks like a mice tails, okay? That galaxies pull off, just like this star you've heard in the news in Corona Borealis, that it's a binary star, that one's pulling off gas from its sister star, and it's brightening, and it's supposed to be right now. They're expected anytime, any night, now day, that we can go out and see this star brighten up. Then it will dim back down. Same thing happens to galaxies pull stuff off from each other. The jets that they send out, like I said earlier, is it far away and bright or up close and faint? We can start actually calculating distances a lot better. And the mass. Because we cannot see the black hole at the center of our galaxy for all the dust and gas between here and there. But we can see through it with Webb. And how things are, yes.
So you're saying that the black hole is at the center of all galaxies?
That's what they believe. And there's some also that are like just the rogue planet that they talk about. There's some out there that just happen to be not at a center of a galaxy. There's stars that still go nova. So
They help galaxy form.
yes, ours. So basically, a black hole, you don't see like nothing there. Basically, you only see the effects. We don't see the wind, but we see the leaves move. That's the same principle. Think about as I said earlier, as a star goes through its cycle of fusing hydrogen and the helium, lithium on down, when it gets to iron, it can't fuse it, all right? As it goes through this, it goes through a process of expanding and collapsing between gravity and pressure, gravity pulling in, pressure pushing out, and it puffs off gas. When it gets down to iron, if it's big enough, unlike our star, it will go supernova and explode, and it will send out all these rare elements. Our sun won't do that. It will become a white dwarf and just keep burning for millions and millions of more years after that. And that's what this star is that they talked about, finding like a close star around the white dwarf. They call it a dead star, but it's still a star burning less. Also, as they look at stuff, they can see that galaxy clusters are linked, okay? What's in between them? We're part of the Virgo cluster of galaxies. Andromeda is our closest sister at 3 million light years away.
So they can actually see those links with
Well,
the James Webb?
well, yeah, and what they're doing, they're looking at the different wavelengths, and they can see strings. It's like if you look at the United States at night picture, you can see the bright cities, then you see it taper off till where you see a few lights, then it goes to the next city. Think about those kind of filament things like that. That's what they're picking up. The Eagle Nebula again. Infrared with the Herschel telescope. Okay, we can't see in here, but you can see a lot more stuff now in the infrared. More stars. Looking back, okay, it's going back way back, just a few million years after the Big Bang. So we're going to see the oldest stuff with the Webb. Move along. Okay, planets in our solar system. We're going to be studying them. Okay, took a picture of, oh, that's the one I forgot to move. That was in the wrong spot. Sorry. Exoplanets, those that are outside of our solar system. Okay, we know there's lots of them. There's a telescope that's out there just dedicated to finding them. And they found thousands of these planets. And one way is that as the planet goes in front of a star, it diminishes the light just a minuscule amount, but detectors can see that. And they can actually figure out how fast is it going around, and they do some more calculations, and they can kind of figure out the masses of them. Okay, so that's the transit method. Okay, you can actually see it going in front of it. There's others, like at the Olympics, that hammer throw, or the, what is it called, the hammer, where it's on the ball on the cable, where the person spins around with that, then lets it go, the hammer throw. I think that's what it is. I can't remember. If you notice, they never stay in one spot. They kind of wobble around as they're spinning around because that 32 pounds or whatever it is pulling them. So they don't stay centered. Same thing happens with planets and stars, that the planet gives some tugs on a star and makes it wobble a little bit. That's another way. And then we'll look at the spectra, like I mentioned. What's it made out of? What's its atmosphere? Okay, dwarf planets and Plutoids. Those are some of the exoplanets that they've been finding. Quaoar, wherever it's at, you know, that was the one of the more recent ones that was a debate on how to pronounce its name. Thought that was a graphic, I guess. Okay. Thought that was a graphic there, but just reiterates what I said. But on the bottom here, so it's going to look at its atmospheric characteristics. Galaxies. See what's made up of, what's in their atmosphere, in the dust, in the clouds and stuff. Okay. Hydrogen, water, just like that one planet thing I said. I don't remember actually, I think I have it on a slide coming up. But what really is behind causing this gas to collapse? We really don't know yet. Is it a shock wave from another one? Well, where did the first one happen at? Habitable zone, the Goldilocks. Okay, we're in the right spot for our star. Okay, maybe we'll find some other ones around these other planets. They found the planet around the closest star that was in the paper this past week. Okay, so all these observations, and it's going to take more than one, okay, to really nail it down. You're going to have several observations and collect data, see if it changes over time. How much dust from that star is left over can make planets, okay? And there is 3 images, 3 different telescopes there. The Hubble on the right, Spitzer in the middle, and Webb on the left, showing the different views of the same object that you can see down to the center. That's why. And there's going to be a ring of dust and gas around stars. Kind of like, look at Saturn. It still has leftover components of it being formed. Origin of life. Did comets really bring water to Earth? Is there any other places out there like us that has water as liquid, gas, and solid? What's going on in the middle there? Why we can't see through there? Because of the gas. And there's the jets that come out, some of these objects, because they're spinning so quickly, especially some of these the stars that are dying are spinning at such a big rate, they actually send X-rays out at the poles. Luckily, they're not coming towards us so far that we know of. All galaxies. Oh. So 2008, before this one was taken pre-Webb. And so they'll be seeing what really is going on there that we can't see with that. This is the very large telescope down in Chile. Okay, so it's going through the atmosphere. Even though it's high up and dry, we'll still have a better image when they put Webb on it. And there are some planets here in this ring going around the star. Omaha. In our own solar system. You know what planet that is? Jupiter. And the Great Red Spot. And we can see that with the telescopes at Orco down at UMKC. We can see the Great Red Spot and the banding. Well, they can actually they can't really do a lot of infrared. They can do some, but also they don't have any propellant in it, from what I understand. So it's out there a ways. So I don't remember exactly its orbit, but I don't think it's going to be crashing on us. Okay. There we go.
But it is still staying.
It's still there, yeah.
And
Hubble will eventually decay.
is it gonna be,
Oh, it's a 10-year mission, but look, it could go a lot longer. It all depends on how things go with it. I mean, look at the rovers on Mars. Some of them are still going. They were supposed to be, what, 90 days? And it's been how many years? Also, not only Saturn, but Jupiter, Uranus, and Neptune have rings. Okay, and so here's one of the moons of Jupiter. Okay, and aurora happens on all the other planets too, just not on us. So it's going to be looking at, now Venus, especially Mercury, is going to be tricky because it's so close to the sun. But everything else, you bet they're going to be looking at it in different and new understanding. Some of the images from Webb. This is in our galaxy, the Sagittarius arm. This is Carina. That's a gas cloud. All that is hydrogen gas. Here it is in different visible light, infrared. This is a big object too, so you'll see how many areas of it in just a moment. This was just in the news. I read it just this afternoon that they think this is orbiting a dead star, but what I was reading, it was a white dwarf. Okay, so it's the same thing as going to happen to our star. It's not really dead, but it's not large like ours. But ours will go the same fate. And they think now that is one of the closest ones that they've.
so the dim one is the planet, like a gas giant?
Well, I think this is the actual artist rendering,
Oh, okay.
because I haven't seen any pictures of it yet. But the temperature is going to be a lot less than what ours is at the same time. Actually, the white dwarf is very hot. Our sun, the clouds, the atmosphere makes it look different. Okay, so there's a whole on the evolution of stars. They're actually, the colors tell us the temperatures. That's the other thing about spectra. We will know the rough temperature of these objects. There's the entire nebula. It's big. In fact, that's 10 light years. So that's about 30 light years across. That's huge. All that gas. Okay. Galaxies. The one in the center explains the different types of galaxies and their mergers. Okay, you've heard of ours being called the spiral galaxy, and you can see, especially in the middle there, where it says normal spirals. Also, they think maybe ours is more of a barred spiral, like this one here. But here's your classical spiral, face on. Okay, we see some of these edge on. So all you see is a band of stars going going across with a bubble on both sides, showing the center. Okay. Here's another one here, 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 here. All those are galaxies except for the foreground. These things here with the crosses will be spikes from the imaging system, and but everything else is galaxies. Okay, this one here. Has anyone heard of this one? Okay, so that was supposed to disappear. So the image on top is actually from a Frank Capra movie. And it's Clarence being talked to before he comes down to Earth to help George Bailey. This is the beginning scene of It's a Wonderful Life. They use Stephan's quintet as the galaxies speaking as the angels. That's an even better image than we had earlier. That area is this here. And you see how many galaxies come in to view from that little spot in the sky. And that spot is, if you held your hand up to the sky, your finger would be covering that many times more. That's how small that is. Black hole. Now they're imaging the effects of black holes. That one, 32, let's see, 32 trillion, 32 billion light years. I should read what I wrote. 32 billion light years. So that took 32 billion years to get here. And you say, well, if it's 13 million years, don't forget the expansion from one side to the other. Between the nebula, 7,500 light years that we were looking at earlier with the Webb. I forgot the name of this one. This could have a star here, could have puffed off all this gas during its life cycle. And eventually this will disappear or go into new stars. By the way, the one on the Eagle Nebula, you can go online and they have the Webbs and they have a 3D animation of it that they put together using the Webb telescope. That's really neat to look at. Really, as far as the discoveries, oh, gravitational lensing. I almost forgot about that. Light gets bent around galaxies and stars as it passes close to them. So, and you can kind of see the effect that it has on the circular effect around some, you look at these long enough, you can see the same image as it's been shifted around from the lensing effect. That's one of the things that they used for Einstein's theory of relativity during the 19-something eclipse, where they wanted to take pictures. They knew a star was here. Okay, during the eclipse, they could see that star because the sun's blocked out, and did it shift from where it was supposed to be? So they could show that Einstein was right. That's just the graphic of what's going on. Einstein's ring. White light, what we would see, and then to compare it to that image we had earlier. Here's another nebula with the central core. White light, half white, half infrared. So you can see the difference. Okay. All this dust and gas here, but then we start to see individual stuff because we're not looking at all this lit up. 65 million light years away. The constellation Eridanus. Hubble, Webb. The resolution and the difference of them. Especially if you look over here, it looks more like the spiral. That's the difference. The list is out there. I started looking at that, well, I need just pick a few things of its discoveries. That's how many have already happened. Okay, there's like a list of about 50. Phantom galaxy. So this is a face-on. There's a mirror image from Webb, mid-range infrared. Now we're actually looking through a nebula back to, I don't recognize the galaxy back there, the image. Now, when we look through telescopes at this stuff, we don't collect enough light in our eye to see color. We see it as gray. And I think about at night, you don't see things in color very often. Trees and landscapes, you see it as gray shades. Same thing when we look. It takes a telescope about 6-7 feet in diameter to start seeing in color of these things, even of Orion. Although you pick out a little bit of green in Orion's nebula. Another infrared. So you can start to discern individual areas, just not a big mass of dust and gas. And then you can start to see the spiral structure as you go around. And Hubble had a deep field, and this was Webb's deep field image. And I know we saw this again. I put these together from 3 different photos showing you the effects of them, of what we see side by side. And this one was the most recent, the one on the far right. It's like turning on the light switch at night. So I encourage you to go out. There's so many websites. Of course, you got NASA's Webb Space Telescope. You have the Space Telescope Science Institute, their website, because they control these things. There's even another web. Just do a search on James Webb, JWST. There's one I found was dedicated to nothing but high resolution images. Lots of them. So we don't have to go to a library and get a book, although it is get a book. I'm talking about the way many of us used to do it by going through the card catalog and taking a look. These are the books that they have at the library. The Space Telescope images that reveal our cosmic history, Webb's universe, and The Infinite Cosmos by Brian Greene. He's a popular astronomer and writer. So these are brand new, and they'll be available. And how long is the checkout length? Okay. These can be checked out in a month because I have them right now. But they told me they were brand new. They just got them in at Oak Grove, in fact. So use your library here. That's it in a nutshell. I mean, there's so much. It's unbelievable what's out there already on it. And it's been so successful because I can imagine if it didn't open and work, what it would have done to the space and astronomy community. They probably wouldn't let us put anything else up again. I don't know. 30 years, $10 billion. That's a good chunk of change. Like I said, over on the table, are these solar system cards. If you want to take a look, this is you can find this on the internet also. This was the media book that NASA put out a few years ago when all this started. And it's still out there on the internet. And then there's some items over there, some different stuff. So, and then our poster from the JPL on the back wall.
Thank you, Joe.
Well, thank you.